Sometimes when people are using R, it's always best to also know how to do it in Excel. The reason is because you know how to do the R, but you're not doing it in Excel. So it's nice that you know how to do it in Excel. So that is the best place to start. However, Excel doesn't have the ability to handle the categorical variables unless you code them. So in the data set, you see that I have some Excel sheet called Brukutu coded. You guys see the Brukutu coded? You normally use that to try to see how Excel will receive the rest. Do you guys see the Brukutu coded?
Yes, Doc.
All right. So just note that you have the opportunity to deal with that Brukutu coded, whilst at the same time, you are dealing with the Brukutu for R. All right, so where is this thing? So you can generate this thing in Excel, but the thing is that you need the coded. So I'm just assuming that you've been able to run this one. You've been able to do the library mass, the ginger plot. Please, Emily, have you done the contingency table?
No, Doc, we didn't do contingency.
So this is a contingency table. So let me see. So you've done all of these graphs. All of these graphs on the screen, have you done them?
No, Doc.
So which one were you doing with them?
Okay, Doc, we did the descriptives and then the correlation and its graphs.
The correlation and its p-value.
Yeah, we did the p-value also, and then the graphs for the correlation.
Oh, that correlation graph, that one is not even important.
Okay.
All right. So guys, let me just give you some important codes to use because this will come in your assignment. And it's important that you know how to go around it. So I've given you a code on the page. This is known as a correlogram or correlation contingency table. Please run and see whether you get the same contingency table that I have on my screen here. Because in your own, you have a contingency table that involves a lot of groups. And you should be able to know how to generate contingency table and explain it. So you can see that in my contingency table here, you have the entire table of Buddhists. You know, you can actually detect how many Buddhists are fishers, how many Buddhists are teachers, how many Muslims are traders, and all of that in the rural area. And you can also tell those that are in the urban area. So please run that code and then let me know if you have been able to run it. Okay. That is a cross tabulation table. That is a cross tabulation table. Let me know those who are able to do it. These are all preliminary things before the actual regression. Actual regression analysis. Remember, the essence of regression is to establish the relationship. So let me see those who have been able to generate that cross tabulation table. It's also nice to, okay, Abdullah has done it. There are some few graphs that you also have to familiarize yourself with. I've just put some graphs there. These are so simple that I thought that you know them already. Checking whether
we did it the last time in class. That's why.
Okay. All right. So you said you generated some graphs I'm about to show here. So let's see whether you generated these graphs. So you can generate kernel density graphs like this. All right. So now, anomaly, I can see that you've done it. Generate kernel density graphs. Do some kind of, there are several of these graphs. You can generate the groups. I mean, he says you've done it, okay? But I'm still going to put these things there. Oops. I'm still going to put these things there for you in case you ever need to do them, then you know how to do them. Just so in case you ever need to do them, then you know how to do them. But you should be able to generate correlation matrix and all of those associated activities. Okay. Let's go to the correlation. The correlation, Emily did generate the following. Let me just confirm. You have to use a package, and then from that package, you are able to generate the correlation. Emily, the correlation, you generated the one that has the upper part chopped off, isn't it? Or you generated
we did both. We did both.
Okay. So you guys know how to generate the correlation with the upper part chopped off and the one without the upper part chopped off. Is that it?
Doc, my own, the upper part was not chopped off.
Okay. Emily, you said that you showed that.
Yes, Doc, I showed it.
Okay.
I've even given the code to them.
Yeah, this is a code in case you don't have it. Yes, I'm just again dropping that for you. This is a code. But this is a correlation matrix that she's talking about. This is it. It's here. Okay. So this one, the upper parts are not shown. And you can have ones where the upper parts are showing the other way. And then its corresponding p-values are here. We've gone through correlation, haven't we? And even interpret it and determine whether it's significant or not, isn't it?
Yes.
Okay. So now we're going to go into the regression that you generated. So guys, follow me. That's the most important thing for today, the regression. I'm going to start it with you. Just so that, I don't know, one professor is calling me about your class. All right. So the first thing to do, and you can see this in the slides, and I just want to go to the slides and show you. One of the first things to do is to be able to generate a simple regression plot. And you can use this command to do it. In your code, you have it. This is a simple regression plot. I'm about to do it here. So please do this along with me. A simple regression plot. This one, it will give you this graph on the right. If you are able to do it, the simple regression plot, using this command, which is also in your slide, if you're able to run it, let me know. If you're able to run it, let me know. Just say done. If you need a code, indicate, let me know. If you're able to run it, let me know. And if you need a code, let me know. If you get it done, just let me know as well. It's done. Who else is done? Who else has been able to generate this line? Who is having a challenge? Who is having a challenge? Somebody says he needs the code. No problem. No problem. Just give you the code. I'll put it here for you. I'll also put it there for you just in case. Who else has been able to generate the simple regression line? Now, in this simple regression line, you will see that there's a negative relationship between the quantity demanded and price. As the price is increasing, the quantity is falling. So there's a negative link. It also has a scatter plot and a fitted line seated between. There are other beautiful plots that can be generated, especially when you're doing your long essay, your thesis, or your dissertation. To do that, there are some packages that one can run to help you do that. If you look at this one here, there's a Gingin plot. Okay. So watch this. There is a Gingin plot. Okay, these are for correlations. Here, that can put a jump point and a polyline. Okay, onto it. It's a very beautiful line, you know. And then you can now wrap it even across groups. You can do that. So you can copy this command and run it. That will give you this graph on your screen. The good thing about this one is that it will add the regression line automatically to it. Okay. But to do that, it will require that you install a package. I mean, I don't know, but some of you may have to install a package. Okay, so let me try this and see. You may have to install a package. As you can see, that mine didn't run unless you install the package. These are two packages that you can install. Now, again, this is just for beautification. Okay? It's not by force. So you install the two packages I've given you there. In fact, I can put the two packages also here. Even though it's on the group, I've also put it here. So once you install the package, then you library it. After librarying it, then you can now run your Gingin plot. Okay. Now you can see that my Gingin plot is showing nicely on the right. The one you have in the note, this will show. So in your note, before you run this particular Gingin plot, remember to install the package. Let me know anybody who is able to run this Gingin plot graph. It's a simple regression graph of price and quantity. And then you can see the wrapped grouping regression line. And you will see that Y, which is the quantity demanded, is a function of price. And you can see that the price is negative 14.3. That's the price, negative 14.3, which means that there is a negative relationship between the quantity demanded and that of the price. After running this command, okay, you can now run the regression itself, the regression result. And to do that, you have it in your slide, by the way. I just ran mine here. And you can see that with mine, you have the entire dependent and independent variable. Now, if you check here carefully, you see that the only independent variable is P, which is price. If you check the coefficient, you see that the coefficient is negative 14.263, exactly what the line showed us when we use the jump plot. Again, it just shows that a 1 unit increase in the price of gin, holding all other factors constant, will deplete the quantity demanded of gin by 14.263 units. That is what it means. But we'll come to proper interpretation when we have included all the other variables. Remember, regression is looking at the relationship between a dependent factor and multiple independent variables. Who has been able to run the graph and then the entire regression table, like I'm showing mine here, and then the graph on the right? Who has been able to do it? Let me see. If you have been able to do it, say done or raise your hand, because it helps me to be sure that some of you are following. Now, of course, if you are driving, there's no way you can do this. If you are driving, there's no way you can do this. 2 people are done. 5 people have shown their hands. Okay, I'm taking note. Don't let me post this thing somewhere, then you say, oh, Doc, me too, I raise my hands. I'm taking note. So I'm taking a screenshot of what is happening. All right, let's continue. So once you've been able to do that, you can show some of the results. Now, there are some other things that one can do really with this result. We'll come to the proper interpretation of the results, as you can see here. Now, this is just to show you a simple regression plot. Now, there are a few important things to note, even with a simple one, and that is a fitted one. You see, when you have gotten the regression line, you can find the fitted numbers. What are the fitted numbers? The fitted numbers are the predicted values. Remember, if you can remember our derivation that we did the last time, where some of you thought it was hidden. We had the Y, which is actual, minus the Y cap. This Y cap is a fitted or the predicted value. This Y cap is actually the beta naught cap plus the beta 1 cap with the XL, with the independent factor. So that is a Y cap there. The Y cap is a predicted value. But the actual value is the one you took from Excel and then took it to the software. That's the actual value. So if you can do that, question is, what is the difference? Let's take the first one. But let's plot them. Let's run the fitted. Okay, let's run the fitted for the Jensen. Look at the values. Look at the values. Look at the values. So let's take the first one. The first one is what? For the quantity is 161. That's a fitted, though. That's a predicted. What was original? What was original? Just let me take you to the Excel, the original. You see, the original was 160. But then the fitted or the predicted is 162 quantity. So what does that tell you? That there is an error. Is it a positive error or negative error? Is it a positive error or a negative error for the first observation? Oh, you guys can't hear me. Can't hear me.
Yes, Doc, you can.
So what did I say?
Because you asked if it was a positive error or a negative error.
But you don't know the answer, eh?
No, please.
You don't know.
I think it's positive.
You don't know. All right. So you can look at the next one, which is 204.95. You compare it to the original. The original is 200. So there is a positive error of 4. If you look at the third one, the predicted is 176. The actual is 160. So again, there's a positive error of 16. Now, this error will all be reflected when you run this residual simple, residuals. That is it. Okay, you give the residuals here. Let's run the residuals. It will give these values. Okay, so I think I swapped it. So you get the actual is more than the predicted. So you get a negative. So you can see the errors here. The errors are all shown here. So some of them are positive, some of them are negative and all that. There was a question. There was one of the assumptions of regression that says the expected value of the error term should be 0, which means the mean of these errors should be 0. How do we prove that? Look at the code that I have here, and you have that code too. Okay, you have it here in your slides. Let's run this code to check whether the mean of the residuals is actually 0. I just did. Let me run it again. Okay. So this is the mean of the residuals. Check here. You get negative 4, 4, blah, 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 e minus 16, which means that there are 16 zeros before the 4, the negative 4. So you have negative 16 zeros. After the first 0, you bring a dot, which is approximately 0. If you have 16 zeros before a number, it means that it's almost 0. So it means that the mean of the error term is truly 0. You satisfy that. You can even generate a confidence interval and the ANOVA table by yourself. So those are the basics of the regression that you should know about. All of these are in the slides. And then you can check the performance of the model. The performance of the model. How do you check the performance of the model? You use something called the R-square, okay, which is a residual sum of squares, the regression sum of squares divided by the total sum of squares. The R-square actually tells you how much variability is in the regression data point. It's also called the coefficient of variation, the coefficient of determination. It tells you the percentage variation in the dependent variable as a result of all of the independent variables. The percentage variation. Now, R-square, if it is smaller, is not good. You want it to be bigger. But it doesn't mean that all bigger ones are best. Sometimes an R-square can be small and it's still good. When you are criticizing the papers, criticize their use of the R-square. 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 Okay. So R-square is supposed to be big, at least 0.5%, 50% or more, according to Herr Black et al. It's good. It's good. It's good. That doesn't mean that the others are small. There are a lot of factors that will influence the R-square. So let's say that you have an R-square in the one we had. Look at the one we generated. Look at the value of the R square. It's down here. It's called multiple R square. You can check yours. It's 75%. What does that mean? It means that 75% of the variability in the quantity demanded of gene betas has been explained by the price. In this case, price is the only independent variable. So price has explained 75% of the data, which means the model is well fit. That means the model is well fit. That's the R square. But there is another R square known as adjusted R square. The formula for the adjusted R square is provided on your screen here. Okay. To calculate it, you just need some things like the sample size and then the number of independent variables, which is a K. And then you need the R square itself. And you can use that to calculate adjusted. The adjusted R square is useful when you are comparing a particular model with another model. So suppose you have two models and you want to know which model is the best. Then you can now check the two of them, their R squares. The one with the bigger R square is accepted. This is very useful when you're doing machine learning or AI related projects. But really, what is adjusted R square? Note this down. But that adjusted R square penalizes the inclusion of irrelevant variables. It's not in your notes, so you may want to write it because I have questions on it. It penalizes the inclusion of irrelevant variables. So if you include an irrelevant variable, the adjusted R square will be lower than the R square. Okay. So let me ask, what if the adjusted R square is equal to the R square? What does that mean? Who can tell us? When the adjusted R square equals R square, what does it mean?
Means that there is no irrelevant variable in your model.
That's it. But I've set a question like that, so you should take
Thank you.
There is no irrelevant variable in the model. Very good. Now, we can also draw some beautiful regression results. For example, there's a package in your lesson called Broom, and you can use it to generate a new form of the R square, a new form of the regression, Broom. In fact, you can even show a 3D graph. But first, let's do the Broom. You have it there. So if you can do it now, fine. If you can't do it now, okay, that is also fine. But Broom, this is it. Oh. So this is my Broom. Okay. If you look at my Broom here, look at it. It gives you the R square adjusted, and it also gives you the R square, the sigma. It gives you the sigma, the statistic. It gives you the p-value. It gives you the degrees of freedom. And guess what? It also gives you the log likelihood information, the Akaike information criterion, the BIC, the Bayesian information criterion. It gives you all of the various, statistics that are used to determine the efficiency, the efficacy, and the reliability of your model. It gives you more information that you will need. Okay. You should check some of these things and then read more about them. It's very useful, to show to reader the implication of them, because that shows the level of knowledge in understanding this. But just note that these last three, they all behave equally, similarly like the R square. They all tell you approximately the fitness, the reliability, and the efficiency of the model you have built. So it gives you more. The Broom gives you more information. Very good. Now, when you have gotten your entire model, you can look at the performance of the model. Okay. For example, when you go back to the one we had, the model's performance is determined by so many things. You have coefficient, you have this, you have this, you have that, you have this. So there are several things. And one of the things that you will need is the standard error. Okay, I'll come back to this when we get to the multiple regression. The standard error is the variability. Emily, you have a question?
Yes, Doc. Okay, so for the Bloom one that you did, under what condition do you get just up to the p-value?
Under what condition do you what?
Okay, so my output was only up to the p-value. The rest that you showed was not part of my outputs.
Oh. Check. Sometimes you have installed a package, right?
Yes.
And you have libraried it out. And after
Yes.
the room, you had a double colon.
Yes. I got the same results, just it stopped after the p-values. So I didn't get the DF and the rest there.
Could it be that you're not getting more space like that? So you have to stretch it to get more.
Okay.
Sometimes I'm not saying you should do it, but sometimes by restarting your work, you're able to get it.
Okay, Doc, thank you.
All right. So, how do you get the meaning of the variables? Now, please note something. When we go to the results, I'm going to my original results here. Watch it. The estimate, write it down, divided by the standard error. The estimate here, divided by the standard error, will always give you the t-value. This is very important. Very, very important. So whatever is here, divided by whatever is under the standard error, should give you whatever is under the t-value. The standard error can help you get the p-value, because once you have the t statistic, which is also called the t-value, you can now read that on the t-table, and you can find the p-value. And as you know, the p-value tells you the error you have actually made in the research. And so you want the p-value to always be smaller. The fact that there are stars, 3 stars, mean that whatever is the estimate, that independent variable is statistically significant at 0.1%. 3 stars. Statistically significant at 0.1%. Now, 2 stars means that it's statistically significant at 1%. 1 star means that it's statistically significant at 5%. That's what it means. That's exactly what it means. But we'll look more deeply on this when we come to the multiple regression, because by that time we have all the other variables. So they will make less sense. But just take note of some of these things. Interpretation is very important. Before you interpret, you have to check whether the variable is a dummy variable or is a numeric variable. If it is a dummy variable, it means it's not changing. It's fixed. It's dynamic. It's not dynamic. It's static. It's statute. So you cannot interpret it as you would interpret a numeric variable. For example, price keeps going up and down, but rural or urban location doesn't keep increasing up and down. You are either a rural or you are urban. It's not changing dynamically every time. So interpretations matter. If it is a numeric variable like our price, you interpret it as a 1 unit increase in the price will reduce the quantity demanded by 14.2 units, holding all other factors constant. Why reduce? Why reduce? Why do you think I use the word reduce here? Why is it that a 1 unit increase in the price
because they are inversely related.
Yeah, why? Why are they? What shows? What shows?
Because when price increases.
No, don't explain it further. What shows, Jerry?
Because of the negative sign.
Exactly, because when you go to the results, you see, you're speaking from your knowledge, but the evidence is what we need. When you go to the data point and you look at the sign, there's a negative sign attached to the 14. And that negativity is what establishes the inverse relationship. So you got to speak in connection with the negativity value. But that's where the evidence is. That's what I mean by what shows. What shows. So you should learn how to interpret both dummy variables and numeric variables. Okay. Now, you should determine, after interpreting, you should determine whether it's significant or it's not significant. You can use the critical value approach like we were doing, or you can use the p-value approach. The p-value is just looking at the results and checking its p-value. The critical value is using the test statistic, which is 10.68. But when you go to the table, okay, this is it. The test statistic is there, 10.69 approximately. So it's similar to the one that we have. 10.68, 10.6, they are similar. So how do you do that? What I did was to divide this one, the test statistic, by the standard error. That is what gave me the negative 10. So this value is this. This is a test statistic, and this is a standard error. I think I missed the typo, negative 10 here. But it is negative 10 or positive 10, actually, because this is a mirror image. This is a normally distributed approximated value. So it can either be negative or it can be positive. Once you get that, you will now compare that to the critical value. You see how we find the critical value? The critical value is T subscript n minus K alpha. N is a sample size, which is 40. K is a number of independent variables. In this example, the independent variable is price alone. Then you add your alpha, which is 0.05. You now go to your T table and go and read it. You'll get something like this, 2.021, which is lower than the test statistic. So since the test statistic is rather bigger than the critical value, we can reject the null hypothesis of insignificance. What did the null say? Well, you didn't see that it was there. It says that beta 1 is insignificant. That's what it said, meaning that the beta 1 is 0. The alternative say, come on, the beta 1 is not insignificant, it's important. The null says, no, it's not important. It is not important, it's 0. But then our test statistic of 10 is bigger than the critical value of 2. And so we have enough gravitas to reject this null hypothesis at the 5% level of significance. You can also use the p-value to conclude. So I brought both of them. That since the test statistic is 10 and the critical value is 2, or since the p-value is 0 and alpha is 5%, we reject the null hypothesis and conclude that that particular independent variable, which is price, is, statistically speaking, significant. So that is how you use the test statistic or the p-value. For exam purpose and for your own thesis purposes, you use the p-value. You can also use a confidence interval to do this conclusion. This is just a way to tell you how you interpret the price. That is for an individual variable. You can also do for joint. For example, you can take all the independent variables, put together and tell whether all of them combined are significant. How do you do that? You use the F test. The question is usually, are the coefficients jointly significant? Or is a regression model better at predicting the values of the outcome variable? So you have to use the F statistic. That's all we use. And then you formulate your hypothesis. The hypothesis will usually say that all of them are 0, which means all of them are not significant. The alternative would say that, hey, come on, not all of them are bad. Some of them are good. So at least one of them is not insignificant. One of them is good at least. Let's check. Use the F distribution. If you check our own, ours will tell you that the p-value is 0, which means that all the independents combined together are significant for this sample. The next thing to do is that you can do a beautiful graph. This time, not a 2D graph, but a 3D graph. You have it in your slides. You have to install and invoke a package known as RGL. RGL. I just did invoke mine. RGL. After that, you can also invoke a package known as Scatterplot 3D. It's all in the slides. Scatterplot 3D. These two. And then you can now run it. Let's run the Scatterplot 3D. I am checking Q, P, and C. So you see 3 variables. The quantity demanded is a function of the price and complement price. That's what I'm doing. And I want the color to be green. Let's see the result. It will open a new window. This is it. This is a new one. And the beautiful thing about this is that you can make the graph a 2D and also make it a 3D. 2D means that you make it like one line, like it stays here. So in this one line, you can see that there's a negative relationship between price and quantity. The price is the one at the top, the quantity is the one at the bottom right. And the rest are there. It even shows you the line. You can see that when the gap above the line is green, which means it's a positive, the gap below the line is negative. It's below, so it's negative. And you can also make it a 3D. This time, when you add the third variable, complement price, it becomes a surface. So you can click and drag, and as you click and drag, you see the surface. So it becomes a polyhedral, a sort of a surface. You can rotate it up and down, left and right, have a look at it, and all of that. Okay. And you can have a feel of how it looks like. So it becomes a whole surface when it is a 3D. And then you can now go to higher dimension, 4D, 5D. Now you can have a complete sort of a cuboid. That is when you have multiple dimensions leading to multiple independent variables. So this is a beautiful graph you can always draw to some of your students anytime you ever happen to teach regression, and show them that, look, this regression can be extended from one to multiple independent variables. Okay. So that was just a beauty to show. There's another one, which is, it won't give you a clear distance, but it will give you something also like a cuboid. And you can see that, again, it's for 3 variables, C, Q, and P. And you can see clearly that this is how it looks. So these are ways you can now do your sort of regression. Okay. Now, let's go to multiple regression. I'm not going to do R again. I'm just going to now teach you the theory of multiple regression. Pay attention. Any questions so far about it? Any question? PhD 4. We are going to formalize multiple regression. It's a bit theoretical, but it's good for you to know this formalization before you run the application. Number 1, a multiple regression still has one dependent variable or target and multiple independent variables or features. I use words like target and features because I'm speaking AI language. And then it has a latter part, which is the error term, the UI. And I've indicated that there are several names of the error term. I did that the last time. Multiple regression. What makes it multiple is that the independent variables I've highlighted are many. You can have another one like this. It's still multiple, but the independent variables are 2. This is not the same as a cross-sectional regression where the independent variables are just x1. Now, the dependent variable is also called regressand, and then dependent variable is also called regressor. So there are more regressors, but one regressand. Write it down. Now I'm going to ask you some few questions practically so that what I just showed you doesn't become too theoretical. A typical multiple regression is on your screen, and it is dealing with variables alone. And it is where you have wage, and wage is affected by or influenced by education, experience, position, and ability, which I'm sure you all know. But then there are other factors that can also influence wage, which have not been written here. These factors are usually found in the error term, the UI. Who can tell me a relevant factor that can affect wage of a person but has not been captured in this model? Who can tell us a factor that has not been captured in this model, apart from education and experience and the rest?
Hello, Doc.
Yes.
Yeah, so I think sometimes where you are working, so the area where the office is located. For example, somebody who is in an office in Accra might earn lesser than somebody who is going to a rural area to work.
That is true. Location, we call it. Yes, people in London are paid more than people in Leicester or Coventry. Yes, Miriam.
I think also the sector in which one works, whether private or public sector, and the nature of the industry.
How many did you
In the
mention?
public, sorry,
How many did you mention?
I mentioned one, as I expanded it.
Nature of your industry. So rates or nature of industry type. Good. What else? What else can affect your salary? Overtime can also affect it. Overtime can affect it. The type of industry can affect it. So all of those factors are inside the error term, and they are known as unobserved heterogeneity. That's a meaning. Unobserved heterogeneity. Okay. Now let's take another example. Let's say that we have an example of this. Blood pressure of a person is affected by the age, the weight, the stress, or pulse. That's the blood pressure of a person. Age, weight, stress, pulse. Of course, there are so many other factors, relevant factors, that can affect blood pressure of a person but have not been captured here. All of those factors are inside the error. They are all inside the stochastic noise, the random noise, the unobserved heterogeneity. Who can give me one of those relevant factors? Joseph.
Doc, the diet.
Diet. Very good. What else? So let's combine diet and medication and alcohol and anything that enters your mouth. What else? Emily.
Doc, genetics.
Genetics, hereditary. Very good. What else? Jerry.
Oh, other underlying diseases.
Other diseases. Very good. What else? Exercise and so forth. Okay. So all of this can affect the blood pressure and they are contained in the error. Let's take another one here. The quantity demanded of a commodity we know can be affected by the price of the commodity, the income of the person, if the good is a normal good, the advertisement on the product, and then whether the product is a complement or a substitute. Of course, the other factors that can affect the quantity demanded of a commodity. Nobody should mention taste and preferences. So who can tell us other factors that can affect the quantity demanded? Miriam?
The quality.
No. Joseph?
Inflation.
Sorry?
Inflation.
Inflation. So call it expected prices. Different from this price. Expected prices. Good. What else, Emmanuel?
Promotional activities.
What?
Promotional activities.
Promotion. Let's call it advert. Is that not so?
So Doc, there can be adverts and then you can also run promotions on the side. So you can have your normal ad and then you can have the buy one, get one free stuff.
The same similar thing. Similar things. Let's get one umbrella name for it. Advert, which is already here. Shaman.
Number of buyers, changes in the number of buyers or population.
Very good, excellent. That's an excellent one. Population is a very matured one. Joseph.
Seasonality.
Seasonality, excellent. Okay. Weather. The weather can change buying. Emily.
Doc, religion.
Yeah, religion, because in the quantity demanded data we have right now, you can see that depending on what quantity you are dealing with, your religion can affect your demand for some product. Very well, like acquisition. So all of these are factors. Joseph.
And the expiration of the product.
No. You're talking plenty. Yeah, the expiration of the product. You go all this.
Can I explain?
Don't explain. I don't explain. See, I know all of these things. I've done it for years. I know how you are going to explain things. I want relevant. If it's relevant, I'll tell you that it's relevant. Ayoko?
Whether the commodity is a luxury good.
But I'll give an example. What determines whether it's a luxury or not is income. So I've given income pattern here. Okay. Now look at the first one and this last one. They are all wage equation, but one is a model, the other is an equation. The first one is a specified model. The last one is an estimated regression equation. There are two main differences. Don't tell me one. Tell me all the two differences between the first bullet and the last bullet. Emily. Emily.
Sorry, I was muted. Okay, so the first difference was there's no error term for the estimated. And then the second difference was there are now values for the beta values, beta estimates. Yeah.
So the first one, the beta parameters have been converted to numerical coefficients. And then the error term is not available in the wage equation. So these are two things. You deal with these things. You deal with these things, you meet them, you address them all the time. Now, you are sometimes asked to specify the regression model, okay, and estimate the regression coefficient and all of that. What we are going to do is on Monday, I cannot meet you at the time we meet. I cannot meet you on Monday. Do you have a class on Monday morning?
Yes, sir.
Management science, we do.
Yes, Doc.
We have.
You have a class at 11 o'clock. 11 o'clock.
Yes. Yes.
Wow.
Yes, Doc.
What about 8 o'clock?
Public
I mean at 8 o'clock?
No, 11.
What about 8
11:30.
o'clock?
We have 9:30.
Optimization at 8:30.
All right. I don't want to miss Monday. I want to move it to other day. So maybe Tuesday. Do you have a class on Tuesdays?
Yes, morning.
Yes.
The time is from 9:30 to Let's say 12.
So guys, I will encourage you to go through the rest of this. No, this one you can't understand. I need to teach you. No problem. We'll get a better way because we need to go through this together. So we start proper multiple regression in our next meeting, which is going to be next week then. Yeah, no problem. We'll do next week. We're going to do Monday, Wednesday, Monday, Wednesday, Monday, Wednesday. If you, I would have done it online. I would have done it online. How about online on Tuesday evening? Oh no, I will teach you. I will teach you machine learning. So Tuesday afternoon, do you have a lecture? 2-3. You have a lecture 2-3.
Okay, so for management science, no.
Okay. So I want you to look at this regression. This is a specified regression model because there's no number. We will come to understand fully this one for the data set. But you can put every multiple regression model, even simple regression model, you can put it in a matrix like this. See, this is a typical one, and you can write it in a matrix. So I'll create one very big matrix for Y with all the data points in it. I'll create one big matrix for X. The 111 is for the beta naught. I'll create one big matrix for the betas, and then for the error term. And then I will now compress them. Okay. So remember, this is an n by 1 matrix. This is an nk plus 1 matrix, k plus 1 matrix, and n by 1 matrix. So, by now you should know about a lot about matrices that we discussed. But the key point is that these are matrices that can be compressed into that. So when you see the y equals to x beta plus u, this y is representing the whole of this y. This x is representing multiple independent variables, 20, all of them from first observation to the last observation. And then the beta parameter will represent the coefficient for each of these columns. Each of these columns. And then the u will represent the error term. Okay. Now, in your regression, you will do, even in your thesis or dissertation, you will notice that sometimes you have to incorporate mediating variables, interacting variables, logarithms, and squares. Okay. What are they for? Now, if you have to use log, if you want to take some of the regressors, you want to take their log. For example, total asset, you take the log of total asset. Leverage, you take the log of leverage. Sometimes some people do some work on GDP, you take the log of GDP, the log of inflation, the log of that. The idea of taking the log is to impose a constant percentage effect. Okay. Now let me best explain. Let's take, for example, inflation. Inflation is a nominal variable. So sometimes you have to collect what? The real variable, but it's not easy to get a real variable, the real inflation, because the real inflation requires a purchasing power. So when you take the log of inflation, you are just trying as much as you can to incorporate that percentage effect, that effect that, no, this thing is not real, it's nominal. And so there are some variables for them because they are changing significantly, because they rise and fall, their real values are not clear. Such variables, you take the log. So that is why you notice that most econometrics data say you take log of some of the variables. Also, you square some variables. For example, you are saying regression, and regression shows a line. But sometimes the relationship shows a line, it falls and rises again. It becomes quadratic. So you square some of the variables to handle the non-linearity is no longer linear, okay, because it's quadratic or N-shaped. So when the data can exhibit that, for example, take footballers, their salaries. Their salaries should be rising as you are playing the football. The salary of the footballer will be rising. I guess to a point, it reaches a maximum, then that football is more like it's becoming, low form. And then they start reducing the salary. So over time, you see that this variable is not positively sloped, but it is quadratically sloped. Such variables, you got to take the square of them. Some variables, you even have to take a cube, because after coming down, it will probably rise again. Some of them may probably become coaches. So their salaries go down, then they become coaches, then they start going up again. Now we've entered into the world of qubit. So, but all of this must be backed by theory. You don't just put them there and log everything and square everything. No. Some variables, they will require that you interact them or moderate them with other variables. For example, you can look at the effect of x1 on y given the presence of x2. Okay. So how do you do that? So what you do is that you take the two variables, you multiply them each other and create a column for it. So you have a column for x1 like this. You have a column for x2 like this. Then you multiply the two numbers, you create a column for x1, x2. So you go and put this one also in the model and run it. So all of these are different ways you can handle the independent variable. And it is important to know the differences in each one of them. There is a difference between mediation and intervention. Okay? There's a difference between mediation and interaction. Mediating variables are causal sequence among three variables, x to m, m to y. So this variable causes that variable before that variable causes the other variable. Give me an example. An example is that a person's particular medication he is taking will escalate and give him some other disease. And that other disease will also give the person another disease. That's mediation. But interaction or moderating. So you see, there's a mediating and moderating. Moderating means that the effect of x on y is conditioned on the level of the third variable. So let's take an example. So you have an independent variable like this, okay, and it's supposed to affect a dependent variable like that. But the only way it can affect it is through this variable, creativity. So the workforce diversity affects creativity, and before the creativity affects the organizational effectiveness, creativity becomes the mediating variable. It becomes the mediating variable or intervention variable. But the moderating variable comes to work with, it comes to work along. It impacts on. So this one doesn't pass through it, but it also adds to what this one is doing before they will eventually affect the dependent variable. Such a variable is moderating variable. I hope you know all of these differences. You should be able to know them explicitly. So let's take an example of a mediating variable. Let's say that we test if x predicts y. So you can see that x here is predicting y. And then we test if x predicts z. X here is predicting the z as well. Now we can test if x still predicts y when z is in the model. Because you are saying that x predicts z, okay, and x predicts y. So now, if I am predicting y, x, which is this one, if it's predicting y, what if the z is there in that variable? Because we already know that the x affects the z. So if z is in the variable, when y are predicted by both x and z, then the coefficient of the z, which in this case is B. I don't know why I wrote X here. It's supposed to be Z, sorry. This X here is supposed to be Z. Okay. So the coefficient of Z, which is B here, this B, should be significant. Because remember that the Z affects what? Y. But the coefficient of X, which is this first one here, differently, when Z is in the model, the effect of X on the Y is different in the model than when Z is not in the model. And that is the essence of the mediating. So it is in the model, in the present. So sometimes we call something industry-specific effect, time-specific effect, time-specific effect. So we assume that they are all in the model. Sometimes we also call some of them control variables. If the control variables are there, how is this one working? That's a mediation. If the control variables are there, they are just there. How is it? Are they dampening the effect or heightening the effect of the first independent variable on the dependent? That is the essence of the mediation. And then there is this, I've already spoken about this, this dummy variable. A dummy is simply a category. So dummy variables are categorical variables. But there's one simple point on dummy I want you to know, that the number of levels are always more than the number of dummies. Let me explain. So let's say that you have gender. Gender becomes an umbrella dummy. How many levels does gender have?
Two.
Now let's take marital status. Okay. How many levels does marital status have?
3, 4.
4. Okay. Single, married, divorced, and widowed. Okay. So you see that it has 4 levels. So when you are creating dummy, you're going to form a dummy that will lead to 3 dummies, 3 dummy variables. So what we are saying is that the number of dummy variables is always 1 less than the number of levels. So gender, looking at the gender where you have male and female, okay, how many dummies are we going to have?
1.
Yes, we're going to have 1 dummy. And you can easily create a dummy. You can create it in R, you can create it in Excel, and you can create it even in Python. So dummy variables are very, very, how you interpret dummy variables matter. We look at the interpretation when we come to application to our own, okay, where dummy variables. Okay. So here I decided to just create a dummy. You can see that location and religion, they were dummies. So I just say that if you have a religion, a location that is rural, let's call it 0. Okay. And whenever you have another one, let's call it 1. So what I'm doing is that I am dummyifying. It's already dummy, but I'm coding the dummies. Okay. So you can see that here, I've created location for urban. So anything here in this column should be urban. So if it is not urban, it becomes 0. So if you look at this one is not urban. So the first one is 0. The second one is not urban. So that second one will also be 0. That is what gives you all of this. And then you can do the same thing for religion. By religion, you see that there are 3 of them. So the dummies you create for religion will be 2 levels. So I created a religion dummy for Christian and then a religion dummy for Muslim. So it becomes, Buddhist becomes a reference category. It means that anytime I talk about Buddhist, anytime you talk about Christian, you're speaking about Christian in relation to Buddhist. That's what it means. So we can apply this, all of this to our data. That will do next time when we meet. So at least I've been able to go through the theoretical purposes. Next time when we meet, I will just run a multiple regression and it's going to be all interpretation throughout.